Okay, we are going to talk about trig identities and how we can prove different things using fundamental trig identities. These are all identities that you already know, that we've already talked about. So the first ones are Pythagorean identities. Okay, so the main one we've talked about is sine squared plus cosine squared equals 1, right? So that's really the only one that you have to remember. And let me show you why. If you have sine squared theta plus cosine squared theta equals 1. Okay, there's our main Pythagorean identity. All right, let's divide all these terms by sine squared. Okay, what do we get? This is just 1. Cosine squared over sine squared, let's think that's cotangent squared, right? And 1 over sine squared is cosecant squared. There we go. There's our second Pythagorean identity. Okay. What if we went the other way? So we're starting with our basic Pythagorean identity. Now let's divide everything by cosine squared. What do we get? This is sine over cosine is tangent. So this is going to be tangent squared plus 1 equals secant squared. Okay, so there's the two other trig identity or Pythagorean identities other than sine squared plus cosine squared equals 1. Okay, those are the 3 Pythagorean identities, and to me, that's how I derive them. Oh, it didn't work. There we go. You can also think, okay, this is like cotangent and cosecant, and this is the other ones, tan and secant. I don't know. It's hard for me to remember these, but I know that I can always derive them if I need to. Okay, but you are going to need to know how to derive these. And on your next test, one of the first questions is going to be list the 3 Pythagorean identities. Okay, so you're going to need to memorize this one and either memorize these 2 or remember how to derive them. It's not hard to derive them, right? It's one step, so you can do it. All right, the next fundamental identities we need to know are even odd identities, right? So which of these are even? Remember, cosine and secant are even, which means cosine of negative theta equals cosine of theta. Secant is like cosine. The rest are odd, okay? And now that we know a little bit about the graphs, you can imagine that, right? The cosine graph has symmetry across the y-axis. The sine graph, you have to fold it twice or rotate it 180 degrees. So, okay, Pythagorean identities, even odd identities, reciprocal identities. Hopefully these are starting to be like automatic for you a little bit. Cosecant and sine go together. Secant and cosecant go together. And tangent and cotangent go together as reciprocals. And then the last is quotient identities. Let's see if I can move that so you can see. Can't move the mouse. Tangent is sine over cosine, even though I know you can't see that. And cotangent is cosine over sine, right? The opposite. Okay, these together are all the fundamental identities. There's a lot of them. If I'd given this to you a month ago and said, memorize this, you'd be like, whoa. But we've been talking about all of these a lot. Hopefully they're starting to get some intuition about these by now, right? You're starting to say, oh yeah, I can figure this out, even if you just, if I gave you a whole table to fill out, it'd be a lot to just fill all this in. But if I said, okay, cosecant is 1 over sine, yeah, you could figure that out, right? Okay, so now let's use these fundamental identities to solve let's go through some examples here. So here we are. All right, so we want to verify some identities here. Verify tangent of theta times cosine of theta equals sine of theta. Okay, how can we do this? Well, let's write everything in terms of sines and cosines. So I could say, well, tangent is sine of theta over cosine of theta times cosine of theta. Well, these cancel. And I'm just left with sine of theta. That's all it is. Not bad, right? Okay, let's do another one. Verify the following using the even-odd identities. So 1 plus sine of x times 1 plus sine of negative x equals cosine squared of x. Okay, so we're going to start with the complicated side of the equation and see if we can simplify stuff to make it look like this. Okay. All right, so they gave us a hint. They said use even-odd identities. So this sine of negative x, how can we simplify that? Well, sine is odd, right? So what does that mean? That means sine of negative x is negative sine of x, right? That's what that means, that sine is odd, so we can say sine of negative x is negative sine of x. Okay, what would be a good next thing to do? How about if we multiply this out? What if we, use FOIL or use a box thing from CPM? Let's see, 1 times 1 is 1 minus sine x plus sine x minus sine squared of x. Okay, well, minus sine x plus sine x. I'm just left with 1 minus sine squared of x equals cosine squared of x. Is that true? Well, yes. What if I just add sine squared x to both sides? That's my Pythagorean identity. Voila. Okay, so how did I do this one? They gave me kind of a complicated looking thing. They gave me a hint using even odd. But really, anytime there's a minus x in here, we can always simplify that using even odd identity. And then I looked at the complicated side and I multiplied things out. Some stuff canceled. And I said, oh, I can make this look like a Pythagorean identity. So sure enough, I verified this equivalency. Okay. All right, let's do another one. Let's find example 4. Verify the identity secant squared theta minus 1 over secant squared theta equals sine squared theta. What should I do with this? Well, let's look at our Pythagorean identities. Let's see if either any of these will help us. Secant squared minus 1 is tangent squared, right? Secant squared minus 1 is tangent squared, which is what I have on the top here. So I could write this as tangent squared of theta over secant squared of theta. Let's write all of these in terms of sine and cosine. Tangent is sine squared theta over cosine squared theta, right? So I'm using my what do they call it? Reciprocal and inverse. I can't remember what they called it for the fundamental identities. And secant, I have 1 over cosine squared theta. Okay, well, I could write this as sine squared theta over cosine squared theta times cosine squared theta over 1, right? Copy dot flip, or invert and multiply. Okay, cool. These cancel, and yep, I'm left with sine squared theta. Is there a different way I could do this? So here's one way. Do you have any other ideas? There's lots of ways I could do this. What if I divided this into both of these terms? If I split this numerator into 2 terms like this. Well, this is 1. And let's see, 1 over secant squared is cosine squared. Is that equal to sine squared theta? Sure is. Pythagorean identity, right? 1 equals sine squared theta plus cosine squared theta. So there's a different way to do it. There's probably a third way. Okay, there's not really one way to do these. Okay, but let's think of the 2 ways that we did it. One was to use a Pythagorean identity straight away, right, and replace this with tangent squared. And then I used the reciprocal identity and ratio, or whatever, I don't know, that tangent equals sine over cosine. I can't think of what they call them. And then I wrote them out. Cosines canceled, and I was left with sine squared. Here, I divided this into each of these terms and got 1 minus cosine squared, and then I used a Pythagorean identity. In both cases, I'm using kind of a lot of those fundamental identities, right? Some reciprocals, the Pythagorean identity, right? So I need to get really comfortable, you need to get really comfortable with all those fundamental identities so that you can recognize when it might be a good idea to use one in these kinds of problems. Let's do another one. Ooh, now they said so problem example 5, create an identity for this expression by rewriting strictly in terms of sign. Okay. So let's see. Let's write in terms of sine and cosine first. Tangent, so I'm good. So we want 2 tangent theta times secant theta. So let's see, tangent is going to be sine over cosine. Secant is 1 over cosine. Okay, so I want just sine terms, but here's what I got. I have sines and cosines. But I have a cosine squared. Here's a hint. Anytime there's like a squared trig identity or trig function, chances are good, not 100%, but like close, that you're going to use a Pythagorean identity. Okay. All right, how can I write cosine in terms of sine using a Pythagorean identity? Well, cosine squared is 1 minus sine squared theta. There we go. I have written this as that, completely in terms of sine. These are equal to each other, right? So we're really just rearranging stuff, right? These are kind of like puzzles. Okay, how can we rearrange things? So a good step often is that we replace all these other trig functions always in terms of sine and cosine, and then see what cancels, see what squares, okay, see how it goes. All right, let's do another one. Example 6, verify this identity. Okay, sine squared of negative theta minus cosine squared of negative theta over sine of negative theta minus cosine of negative theta. They want us to show that that's equal to cosine theta minus sine theta. Okay, everything's already in terms of sine and cosine, so we can't use that trick. But I do see a lot of like trig functions of negative values in here, right? So let's think about what's positive and what's even and what's odd. Sine is odd, cosine is even. So how can I rewrite this? This is going to be sine squared of negative sine squared of theta. So, okay, this is a little tricky because it's really this whole thing squared, right? Minus cosine of negative theta is just cosine of theta. So down here, we're going to have the same thing. So sine of negative theta is negative sine of theta. And this is minus cosine of theta. Does that make sense? So I'm using the fact that sine is negative, but the way I'm writing it, I have to write the whole thing as negative sine theta squared, because now this is going to become sine squared of theta minus cosine squared of theta over minus sine theta minus cosine theta. Okay. What ideas do we have now? Got to use some algebra, some stuff from last semester to notice, this is a difference of squares. All right, so I could write this as sine theta minus cosine theta times sine theta plus cosine theta. See that? If I multiply that out, I'm going to get sine squared theta minus cosine squared theta. Okay, and I'm going to write this as minus sine theta plus cosine theta. Because look what I got here. This factor is the same as this. Those cancel. Woo. And now I have minus sine theta minus cosine theta, which is cosine theta minus sine of theta. All right, so this took a little bit of cleverness, right? The first thing we had to do was use whether these were even or odd functions. So notice again, we're working from the complicated side, right? Just looking at the initial problem, this left side looks like a mess. This looks pretty easy. So we start on the complicated side and try to make it simpler to match the easy side, okay? So we used even and odd to get here. And now we had to be a little bit clever and use difference of squares to get this. And then we started getting excited because we realized, aha, these are going to cancel, and I'm just left with this negative sign. And if I multiply that by this numerator, I get what I wanted on the right. Okay. Sometimes on these, you just got to follow your nose. You just got to try some stuff. I did not know when I started this how exactly I was going to get from here to here. Okay, but I said, oh, I'm going to try to simplify this one step at a time. Okay, so looking at a problem, if you don't know exactly what to do next, that's okay. Or where to start, just think about what's the next thing I could try. All right, so let's look at this one. 1 minus cosine squared x times 1 plus cotangent squared x equals 1. This looks like we're going to be using some Pythagorean identities. All right, let's find those. Can we use any of these? Let's see. Ooh, a 1 plus cotangent squared. I could replace that with cosecant squared. Or x, I guess, not theta. 1 minus cosine squared is going to be sine squared. Right, remember what I said? Almost always. If you've got some 1 plus stuff squared, or even if you just got stuff squared, chances are very good you're going to use the Pythagorean identities. Okay, you got to know them and have them to refer to. Okay, so let's see, sine squared x, cosecant is 1 over sine squared x. Ooh, that looks pretty handy because now that equals 1. Okay, so these are pretty easy to watch somebody do, right? So I'm trying to give you some of the clues that I'm using to know what to do next, right? So Pythagorean identities, writing things in terms of sine and cosine. To be honest, those are the two main things that we've done so far. All right, let's do another example. Let's do 8. Write the following trig expression as an algebraic expression. What are they talking about? They're saying, let's try to factor this. What if instead I just had 2x squared plus x minus 1? Can I factor that? Yes, I can. I'm looking for things that multiply to -2 and add to 1. So how about 2 and -1? So I'm going to split this into 2x minus x minus 1. Right, I just split this. I'm just factoring this, right? Whatever method you know how to factor, use that one. I'm splitting this middle term into 2 terms, so then now I can use grouping. And I would factor out x plus 1, and I get 2x minus 1, right? I can use that same process here, even though instead of x's, I have cosines. So this is going to end up being cosine theta plus 1 times 2 cosine theta minus 1. Okay? And if you can always check, right? You can multiply it out, make sure that you get the same thing. That's what this is asking us to do, is to treat this algebraically. Even though we have these complicated looking trig expressions, let's just think, oh, what if we just had an x instead? How could I algebraically simplify this? All right, let's look at this next one. rewrite this trig expression. 4 cosine squared theta minus 1. Can I simplify that? Well, what if I just had instead 4x squared minus 1? Can I simplify that? Think about it for a minute. It's not obvious, but we've already looked at this. We could think of that as a difference of squares, right? We could write this as 2x squared minus 1 squared, and then we could say 2x minus 1 times 2x plus 1. All right, we can do the same thing here. We can say 2 cosine squared theta minus 1, or not cosine squared, just cosine, and times 2 cosine theta plus 1. Okay, and we can multiply it out and make sure that we get that same thing. Okay, I think we have one more. Let's see if I do this sideways. I hate wasting paper. It's kind of like a dumb thing. Okay, I'm going to use these side of this paper. All right, simplify this expression by rewriting and using identities. Cosecant squared theta minus cotangent squared theta. How can we simplify this? Okay, so I'm thinking of a few things. We have a difference of squares. We could maybe use that. We also could maybe use Pythagorean identities because we've got squared trig functions. Let me find that, please. Let's look. Do any of these look like they would work? Ooh. I mean, yeah. This one just, like cosecant squared minus cotangent squared is 1. This is one of the Pythagorean identities, right? So yes, we definitely can. We can just say this equals 1 using the Pythagorean identity. What do they do? Yep, that's just pretty much what they do. Okay, and I think that was the last example. All right, so let's go back to this for just 1 minute. These are going to be your toolbox for simplifying these, okay? Pythagorean identities, even odd, reciprocal, and quotient identities. Writing things in terms of sine and cosine is a good strategy. Sometimes you're going to have difference of squares maybe. And using Pythagorean identities. If you've got a squared trig function, almost always going to use that. Okay? Good luck.